Hello everybody, my name is Amartuvshin and today I'll be giving you a brief introduction on the use of artificial intelligence in architecture domain. So first of all, I would like to thank Professor Hyun Kyung-hoon for giving me this opportunity to speak with you. So today's talk comprises of two main parts. The first one deals with the history and the application of AI, and the second part deals with the works I have done using the artificial intelligence technology and some other stuffs when I was in graduate school in KAIST. So let's get started. So to give you a brief introduction of myself, I have studied architecture in my undergraduate years, and when I was studying, I worked for a number of architecture design firms. Then after the graduation, I had decided to go for graduate school for pursuing more in-depth study in the architecture field. As you may all know, the architecture is not very simple. It took many hours of labor and design experiments and the patience, and it demands highly laborious those hours to be creative, and similar to any other design profession, right? So what we know about architecture is extremely complex, and we need to think not only about how it looks. Of course, the building looks very beautiful, but if you think about how the occupants live and travel through this building, and also if you think about the performance of the building, it's very, very complex, and many aspects need to be addressed to come up with a successful building. So throughout the history, the architecture project is become no longer one man's job, and the project becomes very large and extremely complicated. Thus, it involves many different people and parties and companies, and most importantly, the work itself demands immense labor and often requires repetitive tasks in the creation and documentation process. Therefore, architects and designers need a better tool and methods in order to deal with the complexity of the project in an effective and efficient manner. So, architects have been designing these buildings and projects with the use of tools, and the tools have been innovating some methods and how we do this drafting and building things. So this small diagram is showing the rough timeline of how the tools have been evolved, and at the same time the methods being used and what kind of significant breakthroughs or innovations has been happened in the history of architecture. So everybody knows the paper and pen and ink came very early, and what happened is actually if you see the left side of the tool, you see the paper that it became very popular and came to the Europe in early 13th century. And right after that, everybody knows about the Renaissance, right? So during the Renaissance period, the first mathematically correct representation method of perspective has been developed by Filippo Brunelleschi, and right after that, the time progresses and people has been doing all this drawing by their hand using a drafting board, and then wood-based paper has been developed in the early 19th century. And then you will be able to see the modern computer, which was proposed by Alan Turing in 1976. So then a couple of years later, the first commercial computer has came. And since the introduction of computers and the commercial computers, researchers and all these people were able to develop their own idea on the computer to come up with the method. So the first computer-aided drafting methodology came up with the invention of Pronto. So the Pronto is the first commercial numerical control programming system, also known as CAD programming prototype. It's been developed in the year of 1957. So this is this, and right after that, the very famous invention, the sketchpad. So the sketchpad has been developed by Ivan Sutherland. When he was in MIT, he developed this tool with his professors, if I'm not mistaken. So it was a very innovative program that influenced the alternative form of interaction with computers. Then the computers started to be applied in architecture domain, mostly in the drafting and plan and section and facade. But all you know, everybody knows it, the architecture firms were still using the drafting board, even though the CAD program is becoming very, very popular. So the first AutoCAD program has been developed in 1982. So what about this CAD program? The CAD program has made easier to draw the building layouts and building facade and building section, etc. But it still demands a lot of laborious work. So it doesn't change a lot. So artificial intelligence, the idea of artificial intelligence came up around the 1970, proposed by Nicolas Negroponte. So he is, he was the dean of MIT Media Lab. So he's been almost like a creator of this object-oriented design idea and also the recursive function. And he thought about this thing in the design process, how AI could be implemented and could be used as an intelligent assistant. So there's been AI already in the design space in the late 19th century. And then you would see one of the most important method has been arrived, which is BIM. And then all you know is the parametric design tool, the Grasshopper, has been invented by David Rutten, who was a student in Delft in Netherlands, and then he became the member of the Rhinoceros company, Macmillan, right? So there's the rough timeline, and to give you the more sense of how this timeline has been looked and the tools have been evolved in the computational design manner. So you have the perspective, right? So pers means see through. Perspective is like to see through something and then give you the mathematically correct representation of 3D objects in Renaissance. And then you have this drafting board, and you use this drafting board to draw and everything by hand. And then the sketchpad. and later the AutoCAD came, and BIM has been made, and the parametric design of Grasshopper. So, why parametric design? The parametric design actually brought some innovation in the field of computational design. So it was a very good tool to deal with the complex shapes and those repetitive tasks which you see on the top. Everybody needs to redo and redraw everything if you have these tools, even though the AutoCAD has copy and copy paste, zoom and mirror in every simple function. It was very hard to do these repetitive tasks. So with the help of parametric design, designers were able to deal with those two shortcomings with just a simple set of rules, right? So this rule could be encoded in the program, and the time-consuming process is reduced significantly. And also it is the start of reducing the cost of the design. All right. Even though the parametric modeling brought some great potential to reduce the time and this labor-intensive work, it has some shortcomings, which was to deal with the many number of parameters at once and understanding all these parameters holistically. So we need some new tools to deal with these kind of stuff. So AI actually came to the architecture domain. So AI was very efficient to deal with these kind of disadvantages of parametric design. So AI reduced the time. AI doesn't need these expensive simulation and computing power. So AI can deal with all these kind of shortcomings with the use of statistical approach. What is AI? AI is to understand it very simply. AI is the machines uses human-like intelligence, such as learning, knowledge, and reasoning to do some tasks. So computers are very good at doing tasks, especially if it's repetitive or some calculations. And AI is being already used in many different fields of science, such as computer science, linguistic, biology, and etc., etc. So how AI is being used in architecture? In simple terms, as I mentioned before, AI brings the statistical principle with the computation in order to make it better the aforementioned problems of parametric architecture. So instead of creating deterministic model, particular rules and variables, AI let the computer decide the parameters from information collected from data or from the users, right? So once learning is achieved, AI can generate the solutions, not only answering the set of parameters, but also creating result of statistical distribution of information which is learned from the training phase. Therefore, AI disrupts the whole design domain from heuristic to the world of statistics, which means everything was rule-based decision-making before, but using the AI, now it becomes stochastic based on decision-making. Okay, so what we mentioned before a couple of slides, the tools are still being used as just a tool. So labor wasn't being reduced, labor hours and everything was repetitive, right? So this inefficient manner could be solved by the machine learning, especially the deep learning technique. And computers finally could be the intelligence assistant for designers or the architects. So where exactly is AI being used in architecture, engineering, and construction domain? If you take a look at this big network of cloud, I would say, and you can easily notice and the types of AI techniques and which kind of sector in the building domain has been applied to. So, for example, life cycle cost and life cycle assessment, risk analysis, and knowledge management, and etc., and monitoring the health of the building and information management, etc. Everything could be used with the AI technology, right? Genetic algorithms and neural network and fuzzy logic and etc. machine learning. This kind of technique has been used in a very broad sense, broad practice, I mean. While the most widely addressed topics or issues using AI technique is optimization and simulation and uncertainty, project management and bridges and robotics. So you can actually download this, check out this paper and read about this interesting coverage of AI, especially used in the architecture domain. So now I will show you the usage of AI in building architecture domain. So what you're looking at on the screen is the neural network technique used for floor plan generation, right? So this is the thesis work of the guy who called Stanislas Chalot. Maybe the pronunciation might be wrong, but he's from France, and he studied a couple of universities in Switzerland and in the States. So his work deals with the AI, using AI and generation of floor plan. So what he did is actually he trained the algorithm with the GIS data from city of Boston, and then the 1 day and a half later, the algorithm were able to identify the rooms and where the connecting these doors are and how these room spaces are compromised, or how this it's been represented, right? So the left side, the animation shows how it's been done from the training starts from here, and the set doesn't really understand where the room is, and then later on at the training end, the algorithm understands everything perfectly. So after that he uses this user interface to give designers some advantage of generation of floor plan. So he coupled this user interface with his algorithm, and then he will be able to make a floor plan easily. And the right side, you'd see it's a very impressive floor plan generation. So it's in real time, so you can just change the layout of the room, and then you'll be able to generate rooms inside. So what else? Not for this generation of floor plan, what kind of stuff is being done in construction? So for example, the safety, the monitoring, the health monitoring of the bridge could be also done using AI techniques, right? So in the bigger scale, of urban scale, if you take a look at this slide, it's also the methodology part of some kind of study. So the upper part is the traditional process of making a city, designing a city, I'd say. So traditional design starts with the inputs, and the urban designer come up with the design alternatives, and then a lot of people came together and discuss and evaluate the performance of it. And after that, they do analysis, and then it comes to the further phases. So it's very limited. You can come up with only a couple of design alternatives, whereas computational process, if you have the AI-backed process, you can define the algorithms and the set of rules, making the streets and a lot of other stuffs. So he used this method, generative algorithm, has iteration of thousands of design alternatives, and then you can automatically evaluate those stuffs and give feedback and iterate back again. And then once the stakeholders engaged, and they can also give a feedback, and the loop further goes again, and then you can end it up not only one answer, but also the combination, the set of answers you could satisfy your needs. So this is how it looks. You give them the density as a pixel, and then you define the block size by drawing a road network, and based on that you'll be able to make these blocks, and then blocks could be translated into buildings and green space, floor radiation, and everything could be controlled the single program. It's very impressive. So from now on I'll be introducing you my own work. So up until now, it was just the introduction of AI and some significant, interesting work. So from now on, I'll be showing you my thesis work, and if I have more time, I'll be showing you some other works as well. So this is my interest, and I am doing research on urban design, and now I understand it's a big picture that building is a real issue that makes a lot of carbon dioxide that could cause global warming potentially. So almost half of the energy consumption goes to the building, so we need to design better. So there are a lot of issues in the architecture field, and I just want to try to make better buildings in terms of performance, not only by the aesthetics and the economical, political aspects, right? So this is the thesis project of mine. So what I did is I did parametric facade generation using some geometric algorithm. So it comes with like this introduction, goes through the methodology and implementation and conclusion. So I'll go a little bit faster now. So the first chapter is, of course, the introduction. So in the indoor space, the amount of natural light is highly depends on the building window, right? So it's called building fenestration, and then all the building outer wall is called facade. So commonly, the facade of high-rise office building is considered as a vertically extruded glass, and it consists of a number of transparent and opaque layers. It's called curtain wall. So designers usually add these kind of shading elements outside in order to protect from direct sunlight, and also BIPV could be added to the building facade to harvest some energy from solar radiation, right? So when the facade is designed properly, the significant amount of electricity could be reduced. So in the meanwhile, there are a number of buildings featuring 3D facade have been built in a different country. So it was really interesting to me. So in the problem statement was to, in order to achieve successful daylighting, a lot of people a lot of academia person or the construction companies are focusing on only on the window size, location, and where to put it, and the glazing property and the blind, and also the wall, the thickness, material, and thermal property, etc. But no researchers actually try to solve this issue with the use of 3D face to facade, right? So what I try to do is not something look like this. I want something look like this, but performs better in terms of these daylightning and also BIPV performance, right? So I did some literature review, and it's how the parametric facade design has been done, and some people did this tiling method and using the either window or BIPV to come up with the better design. And daylighting performance, as you may all know, daylight is very important, and we can use daylight instead of lightning in order to reduce the electric bill. And you can measure the performance of daylighting using two types of method. The first one is sensor-based in situ measurement. You just simply place the sensors all across the floor, and you'll be able to capture how much daylight comes introduced into the room. And the second one is computer simulation-based method, which is predictable method. So I use this simulation-based method for my thesis. So UDI, also known as useful daylight illuminance, is a computer simulation-based predictive method, and it's defined as an annual occurrence of illuminance across the work plane, where all the illuminance within the range of 100 to 2000. Also, the building integrated photovoltaics has been studied a lot. So one of those studies were done by these guys and also here. So the first study was just to give window in the middle and then try to optimize it. And the second study I found very interesting was the single room optimization of solar panel, and then he proposed 13 different type of BRPVs, and then based on the result, the single inclined canopy design was the most optimal. This is interesting. Then we come into the point where the facade optimization happens. So it's a very broad topic. So people been using optimization method coupled with the AI and come up with the best solutions. So building performance-based simulation is widely used in architecture domain, and it's often called black box simulation because of the costly evaluation of the process and unavailability of objective function. Right? So you don't know what the objective function is and how it's performing inside. So it could be tricky that you don't you don't always go for single objective optimization, right? So you can go also for multi-objective optimization, and it's very applicable for the design problem since those objectives are conflicting with each other, and you ended up having the Pareto from the optimal solutions, not only just one single solution, right? So the methodology So how can I make this 3D kind of shaped facade, which can be very good both inside and also good for harvesting energy? So this is the rough diagram. So you have the initial building, and then you slice the facade into some tessellation, and then you add points on it, and then based on those points you extrude it, and then you connect them using the method of Delaunay triangulation, and then applying materials on the generated surface, and then applying it back to the main building wall. Then you ended up having this 3D faced facade pattern. So I'll show you how it's been done. So in this study, two types of pattern has been investigated. The first pattern is just a single type of pattern, so it's repeated all over the wall, whereas the pattern B, which is the two adjacent rooms, has different types of design, and it makes chessboard pattern. So in the end, it will look something like this. So I'll show you how to make this thing computationally. So once you have the surface, you cut them and then put the random points, and then it's been extruded perpendicular to the surface, and then these extruded points, has been connected to each other by the means of Delaunay triangulation, and later on you apply the material property, which the gray one represents the BIPV, the solar panel, whereas the blue ones are transparent window. And then later, if you lay it all around your tessellation, you'll be having this 3D facade pattern. So why choosing this pattern, right? So why can't you just make something different? Is it really efficient? Maybe you can, if you think about the conventional facade having a rectangular window, it could be just used with the 4 points, with the zero extrusion, and the simple combination of BIPV and window. You can represent anything with this kind of method, right? So this is the test room. So all this dimension, and this study includes two objectives. So I want to maximize the electricity generation from the facade. At the same time, I want to increase the daylight inside of this room. So two patterns, pattern A and pattern B, has been studied, and then each pattern has two optimization. One is just flat and no extrusion. The other one has 3D property, which the point goes z directional. Okay, so shows 4 types of optimization. Optimization number 2 and 4 is 3-dimensional. So how do I implement it? Is it's the simulation. So this is the pattern A on the single room is being simulated, whereas pattern B, having adjacent 2 rooms, simultaneously simulated. And all these parameters you can check in here. So to compare with the normal window, I did base case simulation. So the UDI is covered 65%, and the generation of the electricity by BIPV here is 762 kilowatt hour annually. So this is the optimization, and if you look at the number of UDI, you'll be able to see the each iteration comes with the simulation, and then it loops back, and then using the AI technique, you can be able to capture better solutions. Right? In the end, the pattern A shows all the results, and then if you go here this direction to the left side, you would have a better daylighting, whereas if you go down in this direction, you will be able to capture more electricity generation. So this is called Pareto front. So Pareto front solutions are represented here, and A, B, and C, which is here, non-dominance, have been visualized here. It's interesting to see. You see, non-dominant is very good at electricity generation. That's why it's all blanked out. So this is the optimization number 2. This is actually 3D optimization, and I made this animation by just coding it. So you'll be able to see the UDI is becoming greater and greater. Electricity is also becoming greater. And now the results of the optimization number 2. Again, one of the best results of non-dominance. And optimization number 3, which is the flat optimization, but 2 adjacent rooms. You'll be able to see the generation of this facade. And similarly, I'll be able to capture 20 non-dominants in the parental front, and then this is the result of those parental fronts. And lastly, the optimization number 4, which is 2 adjacent rooms having a different design of the facade. Now you see the total UDI is being increased, and each room has been also evaluated, and you'll be able to capture the best solution in the end. Something like this. So there are only 8 non-dominants being found, and if you see the base case is far behind in terms of the daylight, also in terms of electricity generation. So this is the result of the optimization number 4, and if you just give you the sense of how these daylighting is performed, you see the best daylighting is found in optimization 3. However, electricity generation is very good in 3D optimizations, right? And then the mean daylight and mean generated electricity, you can also be able to check the 3D optimizations are far better than the flat facades. And to give you a comparison, the magenta color is 2D, whereas the blue is 3D. So 3D is always tend to go to this corner, which is slightly better. It's far much better than the other one. So you think about this, the base case, any solution from this area you choose is better than the base case in terms of electricity generation. Anything you choose here, the solution here, is better in terms of the daylighting, right? So if you choose from this brown area, you will be able to design much better building facade than the base case. Both light and the energy harvesting, right? So this is the discussion, and I showed them the 3D facade pattern generation works better than just normal facade. So later on, I implemented this project with the thermal load, which is the energy simulation. Previously, it was only for daylighting and electricity generation. Right now, it's being implemented again with the third objective, which is thermal load, so energy simulation. So it's 3 objectives, and then also being done for optimizations similarly, but in this time I did it in 2 different regions. And then now the Pareto front is not a single line, rather it's a 3D surface. So I also did this. I also coded this visualization of the whole result, and then you will be able to see which case is performed better. So this is the one of the best solution of optimization 3. All right, so since we have a really limited time, we jump into the next project I did. It is an interactive wall study. Kinetic facade, also known as adaptive building envelope, have some ability to significantly reduce the energy use of the buildings while improving the level of indoor environmental quality and having a positive impact on the match between the on-site harvested renewable energy and building energy use. So it could reduce the building energy, and indoor environment quality could be improved by using this. So this is an interactive project. So I came up with the idea of how this interactive wall would work. So I just thought about the simple tessellation, just cutting them as a tile, and then having the small mechanics in here with a small hinge, and it rotates back once you have a motor. So this is the prototype I made, and I'm using a leap motion to detect the interaction, which is the finger this time. So it works very well. And then later I came up with the multiple servo motors. So these are the 6 motors, and I've been using my finger vectors to open up the wall, the panels. So there's a little bit in design development and how it's being made, how it should be look like, and how it's been displayed, and also small details. And then test it out with the number of servo motors, if it's really working or not, and then designed everything in 3D and came up with the small details, and I 3D printed out the whole stuff. So you have the small detail of this connector having the bearings inside, and then making this stuff. So this is how it looks in the final stage. So yeah. The last project I'm going to show you today is FPS map, the special representation method for intelligent semantic service in indoor environment. So this is this project has been supported by Samsung, and it's been presented in some conferences as well. So this is the research overview. Let's say he's in the hospital, but he wants to be in his home. So how can we translate his presence in different room? Maybe the answer could be yes, and we can use telepresence using some cutting edge for digital smart home devices and technologies, right? So how can you make a presence? So tele means a distance and presence means existence. So it's similar to avatar, right? So you just send yourself over somewhere else. So you can be deployed instead of going physically to the next room. So if you see on the screen, it's some small cut from Blade Runner 2049. So his home assistant is bringing a meal, virtual meal per se, and the assistant is just a holograph, right? 3D holograph. So how could you actually send these holograph assistants, and how would you know where could the assistant could stay or exist? So not only these telepresence, but also some other intelligence services is in indoor environment is increasing significantly using variety of home IoT and intelligent robots, such as smart home assistant, caring and nursery, monitoring and prevention, and special indoor navigation and avatar telepresence, right? So we need to do main two things. We need to understand the user, we need to understand, the people, we need to understand the indoor space and what kind of furniture is placed in the space and where exactly it's located, etc. So our work deals with the understanding the indoor space. So there's a problem. So in the academia, a lot of publication is only focused on detection and recognition and interpretation of the user. Where's the user and how could we detect him, right? So the second issue was the spaces that could be studied is very, very simplified. So there are no feature of the space. For example, you cannot be able to know the color of the wall, and then you don't know where exactly this table located at, right? So the number 3 is interesting issue. So the functional feature of the inner space are not effectively expressed. So you wouldn't know whether this guy is sitting on a chair, is doing some task, was working, or just relaxing. So since this chair, the same chair could be used in different purposes, we need to understand the space, whether the room is for studying or like working, or could be used as a relaxing. So our research goal then is to solve some problems. Okay? These problems are understanding the space, and how do we do this is we introduced and function behavior structure map, which is called FPS map, and it's a novel indoor representation method emphasized on space functionality in a complex indoor environment for intelligent semantic services. So the space hierarchy is divided into some areas. So this area has some function, right? So this area is for entertainment, this area is for cooking, or this area is for dining, etc. This area is divided into some cells. The cells are the smallest part. It has some structure and behavior, right? So what is actually FPS means? So FPS framework is coined by Narangerel and others, and it's to analyze the functional features on designed object. So it could be applied anything, not only for this space, it could be applied for any designed object. So function, if you think about the function, it's simply says you can see what is this object for, right? What is this designed object is for. And the behavior, on the other hand, is what it actually does. So it's the attributes derived from the structure. So the structure at the very lowest level it's the components of the object and their relationships. So it's actually asking in the simplest way is what it is, right? So if you think about this cluster here, the function of this cluster is reading a book and using a computer, or maybe it could be summarized as a studying space, right? The function is study. Whereas this sofa in the living room has some structures, whereas the parameters such as the location and the size and the name of the furniture, which is sofa. And also it has a behavior, so it's a sitting behavior, reclining, and lying down. So this kind of thing is the behavior that human actually do on this object. Okay, so this is the methodology, and you see how we implemented this methodology in the real world. So we have this data called SunCG data, and it is the data manipulated and collected from the original physical space 3D point cloud scan data, and then they simplified and labeled them, which is called SunCG data. Right? So based on that data, we use this as a 3D modeling, and then we make the understanding of the floor plan by giving the initial grid and then doing all the other stuffs. Once we generate the cells, then we will be able to identify the area, and then area, the bigger one is the space. So we need to do this 3D model based on this existing data. And for example, this case study here is showing that very simplified room, and it's living, dining, and kitchen areas being interconnected, and also there is a small space for studying. Right? So you can assume, you can just understand it without any help of computers, right? So how do computers know, how the AI know that we are dealing with these kind of stuff? And AI would just take a look at it and understand, oh, this is the place for what, this is the place for that. Okay? So we did some basic study for this. So we first identify the furniture objects, and then based on the SunCG data labeling, we found out the name of the objects, and then later the furniture is being eliminated since we have all the list as a data, and then we did find the floor and then divide it into the cell. Based on the division, we will be able to find the areas, and then you could be also see the centers and then connect them. Now you have the whole network of how this building floor is connected to each other and where does it actually located. And this is how we implemented in the environment of Grasshopper. So you see here, this is the data of the building, and some small algorithms could be used to detect all these objects and label them. So since there are a lot of meshes, we need to sort them. So finding out the walls, finding out the layer of floor, and then now you'll be able to retrieve the simple rooms. So this is the room, small room kind of room. So everything works now. So you find out the floor mesh, but there was some problem in the floor mesh because the SunCG data wasn't really clean. So we need to clean this up and then did some manipulation. And then you need to understand how these rooms are connected. So we need to identify the doors, and then doing some hard coding here. And now, yes, you see here, and this is the door that connecting these spaces. So we will be able to find out all these small objects from the SunCG data. And then the final implementation is something like this. So you can use this method to analyze any given layout, especially the 3D layout, right? So previously, the guy I showed you before, he did the layout generation, but he used only for 2D, right? So this method is very advantageous since it's dealing with 3D layout, and it could be also done in vertically, which means you can do it on section as well. So this type of thing could be used very effectively, and this method could be later it could be trained and then used widely, the use of machine learning technique. And I think that's all, and thank you very much for your listening. Thank you.